All right, so this is another example problem where we're going to use the method of joints to solve for uh, the forces within each of the members of this truss. So we have four members of the truss. We have um, member AB. So we have the force within AB, the force within BC, the force within AD, and then we have the force within BD. Alright, so we have four forces that we're looking for. So in order to determine those four forces, we can use the method of joints. So when we're using the method of joints, the first thing we want to try to do is we want to try to identify a joint that has one known force and at most two unknown forces. Alright, so if we just look at each joint one by one, we can start with joint A. Alright, joint A has three unknowns. It has the normal force at point A, and then it has force AB, and it has force AD. Alright, so three unknowns, we can't use that. Alright, if we look at B, we have one known force. We have a minus 400 Newton force along the y-axis, but we have three unknown forces. So we have FBC, we have FBD, and we have FAB. Alright, so we can't use joint B either. If you look at point C, we have, because there's a pin at point C, we'll have an, a force that will have an x component and a y component that are unknown, and we'll have a force along BC that's unknown, and we'll have a force that's along CD that is unknown. So we have four unknowns, so you can't use that either. And if you look at point D, we have a known 600 Newton force that's going along the x-axis, but we have three unknown forces. We have FAD, we have FCD, and we have FBD. So, all right. So since we have no case where we have where we have only one known force, or at least one known force, and two unknown forces, we need to solve for some of our support reactions. All right. So what we're going to do first is, because we have no joint that is under this condition, we need to then solve for our reactions. All right. So what we can do is we can treat this system here as being a rigid body that has this geometry. All right, and we can treat it as just having the external forces being applied. So this would be point D, this would be point C, this would be point B, and this would be point A. So just like we were doing in chapter 5, all we're going to do is include the external forces on this system. All right, and ignore the external forces and the reaction. So we'll just include Alright, so we'll have these three reaction forces. So what we can do is, we know that from point A to point D is 6 meters away, and we know that our from point C to point D is 4 meters away, and from point B to point C is 3 meters away. So using these values, we can sum all the moments about point C, and we know if the truss is in equilibrium, it must be equal to 0. Alright, so we can then say that this would be equal to negative AY times 6 meters plus 400 newtons times 3 meters plus 600 newtons times 4 meters. So if we move AY to the other side and divide by 6 meters, what we'd end up getting is we'd get 1200 Newton meters plus 2400 Newton meters divided by 6 meters, which would give us 200 plus 400 or 600 newtons. Okay, so we can also use the last two equilibrium equations to solve for Cx and Cy. So what we can do here is we can say the sum of all the forces in the x direction is to be equal to 0. In this case, if we do that, we end up just getting the 600 Newton force minus Cx. Right? So we'd end up getting Cx would be equal to 600 newtons. Oh, sorry, this should be plus 6Cx, my bad. Alright, so it would be equal to negative 600 newtons. Alright, and then we can do the same thing with the sum of all the forces in the y direction. We can set that equal to 0. So if we do that, we'll end up getting A of y, which is 600 newtons, minus 400 newtons, plus Cy. So what we'll end up getting is C of y would be equal to minus 200 newtons. Alright, so now we have all the reaction forces solved for. So what we can now do is we can go to point A, and we can take the free body diagram at point A, because at point A now we have at A we have one known force, which is A of y. Alright, and we have two unknown forces, which are FAB and FAD. Alright, so we're going to draw the free body diagram at point A. So we'll have our point here, and then we'll have AY, which was 600 newtons. Alright, and then we'll have FAD coming out of point A, and then we'll have FAB, we'll say goes into point A. So FAB. Alright, now the one thing that we need to know on this free body diagram is what is the angle theta here. So if we look at our original diagram, we see that we have a 5 meter length because we have a 3, 4, 5 triangle here. Alright, so we can say that our line for FAB would be also go along a 3, 4, 5 triangle. Alright, so we can use that ratio of that triangle to determine what would be the x component and the y component of FAB. So we'll start with the sum of all the forces in the y direction at the joint have to be equal to 0. So in that case, we have our 600 Newton force minus 4/5 times FAB. Alright, so if we rearrange that, we would end up getting FAB would be equal to 600 newtons times 5/4. All right, so that would be 150 times 5, which would be 750 newtons. All right, then we can go to the sum of all the forces in the x direction has to be equal to 0. All right, and we can then solve for FAD. So we would get FAD minus 3/5 times FAB. So if we rearrange that, we get FAD is equal to 3/5 times FAB, which is equal to 750 newtons, or we would get FAD is equal to 450 newtons. Right. Right. So we can continue on to a free body diagram at point D now. So if we go to point D, all right, we will have our 600 Newton external force that's being applied at point D. We will have a we will have our he will have our force that goes from A to D here. So this is force AD, which would be 450 newtons. All right, and then we have two additional forces that are unknown. We have a force that will go up to point C, so I'll say this is FCD, and then we're left with our force that goes from point B to point D, so FBD. All right, FBD again is going to be a 3, 4, 5 triangle. All right, it goes along a 3, 4, 5 triangle. All right, so we can again apply our equilibrium equations to determine our unknown forces. So since our known forces are both in the x direction, we can say we'll use the sum of the forces in the x direction first. So we'll say that's going to be equal to 600 newtons minus 450 newtons. Those are our two known forces. And then we'll say that's going to be equal to plus 3/5 times FBD. Or sorry, it should be minus 3/5, not plus. Okay. All right. So now what we can do is we can solve this. So we'll get we'll get minus 150 newtons. It would be equal to negative 3/5 times FBD. So if we divide this, we'll get FBD will be equal to 250 newtons. All right, so then we can use our next equilibrium equation to solve for FCD. So the sum of all the forces in the y direction would be equal to FCD plus 4/5 times FBD. So what we'll end up getting is FCD would be equal to minus 4/5 times 250 newtons, which would be equal to minus 200 newtons. All right. So what you'll notice is, or what you should notice here is that since we have our 200 Newton force is for FCD has a negative sign in front of it, what that actually means is that we have FCD is actually a 200 Newton force in compression. All right, so what that would look like is just on the free body diagram, we would just have, instead of the arrow being drawn here, that's incorrect. It should be being drawn into the joint are going into the joint. So just the sign on the free body diagram would have to be changed, okay? Or you could just note that the 200 Newton force is in compression, all right? So, all right, so then the last, all right, so we have now, let's see here. We have FAB, FAD, F, FBD, and FCD. The only force that we don't have yet is FBC. So in order to solve FBC, we could go to joint C. All right. So at C, we have C of X and C of Y. So we have those as being negative 200 and 600 newtons. So it would look like this. And we have negative 200 newtons. All right. And then, sorry, let me draw that. There you go. 200 newtons going down. All right, we also have FCD, which we know is in compression, so it should be going into our joint. So this is FCD, and that's equal to 200 newtons. All right, and then our only remaining force is FBD, which, based off of the diagram, must be going into the joint as well. So, or FBC, I should say. All right, so if we sum all of our forces in the x direction, we'll get FBC minus 600 newtons, or FBC would be equal to 600 newtons. All right. So if we go back and we look at all of our free body diagrams, what we'll notice is that FAB is going into our joint in our free body diagram here. So FAB would be in compression. All right, and then we see that FAD is coming out of our joint, so it would be in tension. That member would be in tension, and then FBD would be equal to is coming. If we look at our diagram, is coming out of our joint, so that would be in tension. All right, and then our FCD, we found it to be negative. And it was originally pointing out of the diagram, therefore it would be in compression, and we just talked about that a little. And then we had FBC, we have it's going into our joint, therefore it would be in compression. So that is our so that is the end of this problem. Please practice some of your homework problems, but they follow this exact same procedure where you just go from joint to joint, where you have at least one known force and two unknown forces at most, and you can solve for the unknown forces within the joint. And then once you have those unknown forces, you can go to the surrounding joints and solve for the unknown forces that are left in the truss. All right.